we're now at the last paper in this session, and it's the closing keynote presentation. The presentation is going to be given by what I would call an industry friend, colleague, and someone who welcomed me to the MEMS community, and I was trying to think when it was, probably 20 years ago, and has helped me develop as a person, both professionally and personally. So I'm getting all emotional trying to introduce you here. I have to go back to the script. So we're going to have a presentation from Dr. Dave Monk, who's going to talk to us about new application spaces in automotive, industrial, and medical segments requiring immutable MEMS and sensors. For those of you who don't know Dave, and I'm sure many of you do, Dave received his BSc in chemical engineering from the University of Iowa in 1989 and his PhD in chemical engineering from Berkeley Sensors and Actuator Center in 93. He also received an MBA from ASU, or Arizona State University, in 1998. He joined Motorola in 1993, where he worked for 3 years in sensor packaging, and you'll get a sense that there is a lot of sensors in his bio, in sensor packaging technology before moving into the technical program management of MEMS products. From 2001 to 2005, he managed the sensors R&D at Motorola, and he then moved on to the spin-out of Freescale Semiconductor, where he became the automotive sensor product manager for the sensors business unit. He's then revitalized the program at Freescale, and he then moved on to become the vice president and general manager of the product line motion sensors at NXP Semiconductors. And in 2023, he assumed the position of vice president and general manager of the sensor product line at NXP Semiconductor. But outside of his role at NXP, Freescale, and Motorola, he's also been very instrumental and very active in the community. So today he's very active and holds several roles at the Transducers Research Foundation, and he's also been part of the MEMS Governing Council, where I know that he does have a like of red wine, which links back to Ray's presentation on going into space, because he helped get the bottle of wine, and you told me it was $1 million, that bottle of wine, which I think if you'd realized that when you saw it on the screen, you might be trying to buy one yourselves. But that $1 million bottle of wine went into space, so that was quite fascinating. Anyway, outside of that, he's also worked in several technical committees and really instrumental in what we have today here at MSIG. So please welcome Dave to the stage as our final keynote.
Thank you, Michelle. Welcome, everybody. So for those of you who don't know me, I'm now the MEMS general manager at what was Motorola once upon a time. I've worked for 3 companies, but it's always been here in Phoenix, and it's always been the MEMS business at Motorola. We started in Phoenix, where ON Semiconductor's headquarters is, and now we're in Chandler, Arizona. We've been in MEMS since 1979. I would venture to guess in this room we're probably the ones that have been around the longest. I know there are a few in the Bay Area that were around longer, but we've been in MEMS a long time. NXP, by the way, is a obviously multinational company, does semiconductors. It's really the combination of Philips, electronic semiconductors when Philips spun out and became NXP, and Motorola Semiconductor when Motorola spun out. And I find it fascinating. They're 2 very, very similar companies in pedigree. They both come from innovators looking at things like car radios or lights. Car radios in both cases. They both spun out their semiconductor businesses or created semiconductor businesses, and Dan Noble's the guy that brought semiconductors to the Valley. And I would also venture to say that probably he was the guy that brought all semiconductors to the Valley. Motorola was the first. I know ST had sites here. Now you go up north, you see TSMC, you see Intel building. I think we have something like $50 billion worth of investment in semiconductors here. But you've got Microchip, you've got Amcor, you've got Medtronic, which is a bunch of ex-Motorola guys. So there's a ton of that legacy of semiconductors in the Valley. So what I want to talk about today is really kind of a simple premise. The simple premise is this, that if you want to sensorize the world, you can't do it if you don't have the right quality and reliability. It's not possible. Look at some of the stuff that we just seen. Ray started the event yesterday and talked about various type of sensors in space. Sorry, but we can't put altimeter from a cell phone in that application. It's got to be far, far different quality and reliability to make that. But even in automotive, we work largely in automotive safety. That's probably part of the reason that most of you don't know so much about NXP MEMS, because that's where our forte is. I would also venture to say that none of you want to have the types of issues where your airbag didn't work or where your braking system didn't work. And for a guy like me who's been around a long time, I've got a lot of stories. We'll talk about a few of them where people have come in and have been in accidents on our team, and the policeman said, well, you by rights probably should have been dead, but the airbag worked really well for him. And I found out that was the guy who was the test engineer who made the sensor that went into that application that actually saved himself. So there are more than one of those kind of stories, and those are great stories. I have very motivational stories for us. But you've got to have that kind of quality and reliability, and I'll distinguish the two. Quality means how many returns do you have back? What's your PPM level? Our PPM level is less than 0.5. You have to be at that level to be able to be in automotive safety. Plus, you have to have things like functional safety. Plus, you have to have things like redundancy in the system. You know, a braking system or an airbag system, they don't work on one sensor. They work on multiple sensors to do that deployment. Then there's reliability, and reliability really is about the longevity of the device. And if you look at some of the market reports, we talked about, I think I saw, and you'll see in my talk, we'll be 10 billion people by 2050. How long is 2050 from now? If we're going to make an infrastructure device that's meeting that requirement, that's more than 25 years from now. Are our sensors going to survive 25 years? How many people have a model that describes the humidity performance of a sensor for 25 or 30 years? I think that's something sorely missing in this community. So that's really the premise. That's where we start. The SEMI team asks that I start, however, or at least I present a little bit about the people and what we're doing within NXP in terms of DEI and sustainability. So I'll start there. And I start there because this has really become our corporate norm. When we have a meeting like this, a town hall, et cetera, the first thing that's done is what Kurt Sievers would call an inclusion moment. And that is somebody coming up and stepping up and talking about how including people would create something, would create more collaboration, for example, would create different potential opportunities. What I did was I looked at our webpage with all of these inclusion moments, and I created this word cloud of the various different pieces that people talk about in inclusion. And the most recent one, unconscious bias, is interesting. That's the one that every one of the Motorola NXP employees are being trained on right now is unconscious bias. But I guess I want to start, I don't have Paul Carey's little clicker, but I want to start by demonstrating to this audience the inclusion, the diversity that we have. And it's always been one of the prime reasons why I've stayed in this community. How many people here are electrical engineers? Okay. How many people are mechanical engineers? How many people are chemical engineers? How many people are physicists? Chemists? Oh, geez. I guess I graduated from a college of chemistry, so I'll raise my hand. Business people. Any sociologists or psychologists in the room? My point is, we don't make these devices unless we have this cross-section of people in the room. And I know typically we talk about racial or other types of social diversity, but the diversity that we have in this room is what creates the kinds of things that we do. And what I would like us to get to is extrapolating that to the rest of the use case, the rest of the quality and reliability, by using our experiences in this. Let me make two examples of why this is not just good for society, good for employees, but it's actually good business. So we heard a talk about cardiovascular health. How many people know that the cardiovascular challenges that happen in men are often very different than the ones that are happening in women? And are we tailoring for both? Or are we tailoring mostly for the men where most of the data and the analysis is being done? Also, we heard yesterday about a solution for sickle cell anemia. Sickle cell anemia, I would venture to guess, doesn't happen probably to anybody in this room. But the fact that we consider it as a community and consider the diversity of issues and therefore use our diversity of talents is really, I think, one of the reasons why we can solve these kind of societal issues. Then let's talk about sustainability. Francesca and Sarah talked a lot about sustainability and led right into this. We actually put our money where our mouth is. 20% of our annual bonus goes to this sustainability scorecard. We talk about people, we just discussed that a little bit. We talk about the environment. We intend to be a carbon neutral company by 2035. There's a roadmap to get there from where we are today, where we own some of our fabs and we do some outsourcing to get to that point. And then we talk about the portfolio. And I've been fascinated by the analysis of the portfolio. I'll give one example that we were participating in. That's making a pressure sensor for white goods. Making a pressure sensor to do front-loading washing machines. Sounds like a really easy thing, right? You can do, it's basically 6 millimeters of water go into that. You save energy, you save water, et cetera, et cetera. But how difficult it is to put a pressure sensor in a washing machine. What's laundry detergent? It's alkaline. What do alkaline solutions do to silicon? They etch it. That's how we do bulk micromachining, right? So we made a lot of good flow sensors in the early days when we etched through diaphragms because we didn't have the right protection scheme around the sensor to put in these washing machine applications. So we had to experiment with all kinds of different polymer materials, like gels, to try to protect the actual sensing transduction device to make that work. But that worked in the 1990s, and now for 25 years, we've still been producing that pressure sensor, which saves water, saves energy, et cetera. So my point about DE&I and sustainability and why both are good business. So I'm going to talk a little bit about the history of our business. I'll give a little timeline and tell a few stories about what we've learned in terms of reliability and quality. 4 years ago at this event, I talked about this thing we call above and beyond. I'll talk a little bit more about that because I think we need to accelerate what we're doing as a community, and a lot of this is pre-competitive kind of nature. And going to what I'm describing, immutable MEMS. Immutable, we'll talk about that word. Basically, stable, robust. You heard the word robust earlier today. And I'll give a couple examples in automotive. The transition from the internal combustion engine to the EV, and I got to tell you, as a chemical engineer, lithium-ion batteries scare me. We're about where we were with internal combustion engine in the 70s. Those 5 pressure sensors that, I don't know what Jeff is, that Yul talked about earlier, they're because of the pollution in the internal combustion engine. And we have the same kind of thing going with lithium-ion batteries, and we need to produce solutions for that. We'll talk about industrial example and predictive maintenance, and then I'll give an example in medical and some calls to action. So this is a depiction of the history of MEMS at Motorola, Freescale, and NXP. And I'm not going to go through, I'm just going to pick out a couple just for your benefit. We had our first pressure sensor in 1980 in production. The first, what we call compensated pressure sensor, and the DALSA team still produces this device for us, went into non-invasive blood pressure sensing. So this is the first time we had to deal with what we call media compatibility or chemical compatibility. What is non-invasive blood pressure? You have that little tube that comes out of your arm, a saline solution. Now you got to make sure that the sensor survives for 24 hours in that saline solution. So we did that analysis back in those days. Then we started into accelerometers in the 90s, and I'll give an example there that was a really challenging problem for quite a bit of time. In the 90s, we had an issue with customers where they would mount the device, and depending on how what signals the device got, if they were 8 kilohertz or 12 kilohertz, we would get an erroneous output. Well, erroneous output in an airbag situation is a bad thing, because now you've got your trigger. Remember I said it takes 2 to deploy the airbag, 2 signals. Well, now one of your sensors is already triggered. What we determined from that is that there were some mechanical elements in our packaging and in our entire device that created issues with the actual movement of the proof mass. They were completely unrelated to the silicon design. Dr. O'Brien and I have worked a lot on that problem back in the day. The customers came to us and said, well, that's completely impossible. There's no signal above 2 kilohertz. There's all kinds of signal above 2 kilohertz. We can all hear it when we listen to a vehicle, so we know that. What turned out is their reference accelerometer had a roll-off at 2 kilohertz. They never measured the signal above 2 kilohertz. Once we started measuring it, we started finding the solution, and then we've moved on advancements in the way we do the design that I think all of us now have an overdamped 20, 25 micron thick proof mass, 1 to 2 micron gap that creates an overdamped mechanical situation. All of us have that now, but back in those days, we didn't know enough to understand that point. In about 2005, 2010 timeframe, we started into tire pressure sensing. Tire pressure sensing is another completely challenging device because now you got to put the device, a pressure sensor, into a moving vehicle, and that gel that we learned how to use in medical pressure sensors now creates a signal because it's a mass on top of a moving object. So we had to do all kinds of studies with different protection layers while we still have to protect against all kinds of things, including Arizona dust. There is actually a spec for Arizona dust that we had to pass. But all kinds of other chemistries, salt water, gas, petrochemicals, et cetera, to create that balanced solution. I don't have it on this chart here, but it just as an aside we'll get to make a medical pressure sensor, you need a medical compatible gel. You can't use the same one you're putting in a tire to put into an inhaler for asthma. So there's more engineering that's required in that situation. Then you see, and I think Sarah talked about it as well, you see cross sections like under this 3-axis accelerometer and gyroscope where we have a small recess in the wafer, in the bonded wafer to do the wire bonding. That creates huge problems in our assembly area because now you have a wafer that the assembly guys look, they have a bunch of stripes across it. Those stripes, when you put it into a wafer saw, they're natural places to collect contaminants. Well, that's a bad place to collect contaminants because that's right at your interchip bond where you have those capacitors. So we've moved away from that and for many other reasons as well, come to this solution where we have a through silicon via. Now in assembly, that looks like any other wafer. So if we send it to a subcon, they don't know the difference between that and a CMOS wafer. And that makes their jobs considerably easier. So many different lessons learned throughout this. And one thing that I would leave all of you, and I think Francesca, you talked about it as well. When we talk about use case, we really talk about 3 things. Number one, when the box of the reel leaves our shipping dock until the time it is in the vehicle, what happens? When you make a low G accelerometer and it goes through various different, let's say wire bonding at 120 kilohertz, it goes through some kind of shock. We once had a customer that was using a automatic riveter right next to the low G accelerometer. Well, wonder why we have damage or stiction events with that accelerometer. So you really need to analyze the whole line. So what we're doing now is we're taking laser vibrometers down our line, down our customer's line, even in the OEMs, to make sure that the handling of the device is done effectively. That's number one. Number two, there are repairs that are made, right? In an airbag system, there aren't any repairs. But in a key fob, we make devices for key fobs today that prevent, that are security devices that prevent stealing a vehicle. But in a key fob, how many people have changed the battery in their key fob? That's like 1,000 Gs when you pop that battery out. Oh yeah, and by the way, it's static electricity too. So it's not only got mechanical shock problems, it's got electrical shock problems. So you have to map your design versus that. Then the third thing I would say is the actual use case in the vehicle or in the application or abuse case. I once had a guy, and it was with the big 3, I won't tell you which one, where the guy told me that a tire pressure sensor needed to be rated to 90 PSI gauge. And I said, 90 PSI? I don't know a tire around, a passenger car tire, that's above 35 to 45 G. And it was because somebody in his family had put 45 PSI into an already full tire because they didn't know the difference. That sounds crazy because we're all engineers or we all have technical background, but that's not that crazy. So you have to think about how is somebody going to misuse your device in the application, and maybe that's even more important than the actual use case. But the actual use case, in, for example, a tire pressure, patch-mounted or a tire-mounted device, it's hitting the pavement. It does what's called contact patch. Every time it hits the pavement, another 1,000 Gs. Well, if that's a low G accelerometer, that could be a problem. But can you get by with a medium G accelerometer with much more restoring force? So those are the kinds of design work that we need to do. So this point, immutable. Immutable is a little play on words, but the point is it needs to be robust, but it also needs to be something that is always talking. You know, if we're going to sensorize the world, you want the data all the time. So my comment is about immutable. How do we deal with this, and how do we consider, and why did we consider this? Because 30 years ago, we weren't 0.5 ppm. The problem statement for us was poor quality was not only an issue with launch, an issue with our customers, an issue with brand image, an issue with financial claims, for example, but it was an opportunity cost for us. The number of times we had to pull people back to do quality work on a product that was ramping in production instead of one that's already or working on the next project, for example, was an issue. So we did something where we moved all of our safe launch activities and we pushed it left, pushed it earlier in time. Now that's not as easy as it sounds. It means you have to have your whole supply chain available. You got to go buy all those testers and all that $1 million piece of equipment much, much earlier than, and it's going to sit idle for a long time. You got to convince your finance guys to go do that. So the idea of above and beyond is to try to consider several things. If you qualify an automotive in the AEC Q100, you're qualifying 3 by 80, 3 lots by 80. If you look at the 90% confidence interval, that's maybe 10,000 ppm. You're not getting quality data by qualifying a part. What you need to do is you really need to understand what the risks are, where the failure mechanisms could be, and if you can actually tune those knobs to create the Six Sigma device and test that device in the application, then you're doing really, really well. That means you probably tested the failure, you probably know the failure mechanism and have modeled it. But even if you can't do that, if you brute force test tens of thousands, even hundreds of thousands of parts. Our last qualification of this new technology, we tested over 200,000 parts in humidity, just to try to get to the point where we really understand the performance of the humidity. Then I know I talk to people in the consumer space as well as in the automotive space, this idea of ongoing reliability monitors. We both do it. The idea is that the qualifications at time X, that doesn't represent all time. So you need to do reliability monitors throughout time. And then you need to continue to assess the use case and create your own tests that have nothing to do with the boilerplate. So when we look at stiction, we have something where we take a device and we slap it against the table, and we've created this torsion beam test to look specifically at stiction, because we know that's something unique and AEC doesn't define that. Ultimately, where we were is a lot of opportunity cost. Where we're going is a place where we do that all before qualification. So we've basically got our safe launch done before we started the ramp of the device. So I've given you some examples of where we've been in automotive safety. Now to 3 examples of where I think that this is absolutely critically important if we're going to serve these markets. In the transition to EVs, lithium-ion batteries have something called thermal runaway. We've probably all now seen it in the news. The battery has some aberrant galvanic reaction. How can we predict that that's happening? Well, pressure sensing is one way, but pressure sensing happens after you have multiple Avogadro's numbers of atoms in the cell. Well, that's a lot of pressure, that's a lot of chemical reaction products. How can we get to the point now by combining potentially gas sensing and pressure sensing to do a better job of thermal runaway detection, and better yet, get to predictive maintenance? That's really the ideal here. So our thought, and I think you've heard this multiple points throughout the week, is create some kind of hub with multiple different sensing, and this sensing may not be MEMS too, by the way. We have battery charge controllers that are part of our NXP business, so we look at the charging and discharging of the battery, and as that ages, you know that thermal runaway is more likely. So you integrate that data, you integrate the pressure data, you integrate chemical sensing data, you put together some algorithms to understand whether or not this happens. But to do all that, you have to have reliable data all the time, or else you're not going to detect that's going to be a problem. Then industrial, this is Siemens data. They talk about, for the Fortune 500, being almost $2 trillion when you look at the productivity and maintenance costs of downtime that happens. For those of us who've seen downtime in a factory, it's outrageously expensive. You can send thousands of people home. So how can we fix this? You know, the example of that we looked at for water leakage today could be used in a pump or motor. Can we use vibration to sense whether or not a pump or motor is starting to go out of calibration and needs preventive maintenance before a failure actually happens, and do that more predictively? That's really the idea here. But to do that, you need the data. You need the device to be always running and always working. You need it to analyze the data at the edge, because that's, you know, if you're at ExxonMobil refinery and you have a pump, you're at the edge. You're not probably somewhere where you have all this data. So you need to create decisions on that data. But there's many other places to do that. You know, looking at this chart over here on the right, how many people have heard your car fail before you actually knew it was failing? You can hear the sound. Or if you can hear it, you can measure it with a vibration sensor. But there are other signs of failure as well. There are magnetic signs, there's pressure signs, et cetera. So integrating those signals together, using clever algorithms to do predictive maintenance is something that's going to be required to be in this market. And to be in this market, you know, this is infrastructure kind of market. These markets, the device needs to last 30 years, 40 years, 50 years. You don't want the device to be the predictive maintenance. You have to pull it out. You want it to be there all the time. One other point, we talked about energy harvesting yesterday as not being ready. I would submit to you it's not ready because of this. Because of it, every kind of energy harvesting right now decays over time. That's, if you're going to make a remote device that's battery operated and you have something that decays over time, how can you count on it? It's not ready for these kind of markets. Then there's maybe my favorite, and that is geriatric activity monitor. You see the same stat, 10 billion people by 2050. This one's my favorite because my mom was a physical therapist. And the number of times I heard her say the exact same thing, she always worked with geriatrics. The same thing was, if my patients just did their exercises when I wasn't around, they'd be so much better. We have all that technology, but will an 87-year-old be able to manage it? We've got to make this such that they can manage it and that we can really, truly do remote medicine so that people can get the benefits of those exercises all the time. We have building blocks, pieces of it, but you see, not yet do we have that kind of system together. Obviously, the pandemic proved that there are a lot of respirators and ventilators needed. My kids both have asthma, so smart inhalers is great. The number of times I saw my kids laying down on the couch and trying to give themselves a puff of albuterol, just crazy. Other types of bed monitoring, et cetera. But more of this integrated together into hubs is really required to go address the kinds of things looking at geriatrics cares. Ultimately, what I'd like to say to you is I would truly love, by the time I retire, for there to be more sensing of us than our vehicles. Today, that's not the case. And I find that crazy that it's not the case. So, my summary and call to action for all of us. Really, we have to pay attention to this. We have to have robustness. I use the word immutable, a similar type of thing, to be in these markets. SEMI has a team working on this standard. Please participate. Sixto from our team is leading this effort. I think it's incumbent upon all of us to abide by this and really advance the field to the point where we can participate in these kind of markets. We've got to be connected. Probably very few singular companies are going to be able to come with all of these functions to create these kind of devices. So more and more partnerships where we have machine learning, AI companies working with connectivity companies, working with sensing companies so that we can create these edge solutions. And that's really the point. And by the way, not all of us have all the sensing modalities either. So we're going to have to work together to create these combined hub-like sensing devices. So thank you. I'm open for questions or comments. Dr. O'Brien, I presume.
Dr. Monk, how are you? Great talk, by the way.
Thank you, sir.
Quick question. You quoted a half ppm failure rate, right?
Yes.
So how did you get there? And the question is, was it a natural march with better processes, or did you have Six Sigma black belts going through Pareto's trying to figure out what to optimize?
Yes is the answer. Yes to both.
Yes.
Yeah, of course, when you have an issue and you look at the PPM, you've got to do some kind of Pareto analysis to define where the big hitters are. Now, some of the big hitters you can solve with new processes, right? So we did some of that. But to get to that kind of level, you really got to whittle away the, not just the 80%, but also a lot of the 20% to get to half PPM kind of quality. So yes, we have a significant number of various belts, black belts and otherwise in Six Sigma. We're Motorola heritage that kind of invented that. So we take advantage of a lot of that analysis to get to that level.
Yeah, half ppm, that's the best in the market, right?
I think that would be the way our customers state it, yes.
Thanks.
So Dave, I have a question. You presented here before, and your call to action before was that you wanted us to address reliability in a more serious way. And at the end of your presentation, there was a similar call to action.
Yep.
Do you have a thought on what it would take to motivate the teams to be involved? Because I know that there's reliability for automotive, there's reliability for consumer. I know there's a challenge around the testing around those reliability, but I don't know what it would take to get the people involved.
Well, what I wanted to do today is I wanted to make sure that people see that there's actually business behind it. It's just good business to do it. Money, a smart guy once told me, if you want to know the strategy, follow the money. Okay, well, there's money behind this, so it should be our strategy as an industry group. That's really kind of the thing. If we want to get into these other areas, we're not going to get in there with the kinds of sensing that lasts 2 or 3 or 4 years. It's got to be high reliability, high quality.
I actually see a lot of synergies between what you're talking about from an automotive perspective and being an equipment supplier, what our tools could then take on board to then try and build that into the ecosystem, and then what Sarah presented building in there as well. So really definitely very interesting. So thank you.
Mm-hmm. Stefan?
Dave, thank you for the talk. So if we talk about automotive, I think this relationship and understanding what are the failure mechanisms, how do I have to test, developed over tens of years. If we now look forward for new applications, we are going medical, we are going in space, we are going whatever.
Yeah.
This has to be re-adapted or relearned. How do you think can we get in a faster learning curve on these new applications?
Yeah, the analogy I would bring is what the CMOS industry did. A lot of times we get criticized as an industry of being so far behind in our maturation versus where CMOS was maybe 30 years ago. But if you look at the way CMOS developed, there were pre-competitive groups that were working on gate breakdown voltages, et cetera. And they were working across various different organizations. I think we're going to need to do more of that kind of work. When you go into space, we don't do rad-hard devices, so we would need to learn from others as well. There has to be that kind of collaboration, Stefan, and I think that's really what's incumbent upon all of us to participate. To Michelle's point, we've got to participate together to create this pre-competitively, and then go make the devices and compete. That's fine. But this type of stuff is what's going to propel the industry, and I'd be glad to work on robustness validation with Bosch.
Yeah, I think we have to develop this, and I agree what you say, but you have seen in the example of Francisca, sometimes we have to think beyond, so it's not on the sensor itself. Maybe the reliability has to be also done in the implementation of the solution.
Absolutely.
And that makes it probably more complex also in future to have the best solution in place.
Yeah. Well, and you're absolutely right. There will be use case specific topics that are product specific, like Francesca pointed out, and the integration into cell phone that probably we're not going to worry about. But there are other more fundamental types of topics. If we're going to be in space, we're going to need to all worry about how do we create radiation-hardened devices. So we'll have to distinguish between the intrinsic and the application. Yeah.
So let's thank Dave again.
Thank you.